and electrostatic discharge protection, wiring, corrosion protection, some devices, of course, and there are additional applications, sensors, batteries, smart windows, etc. And all of these are can be classified as electrical, optical, and magnetic material properties. And you can see that one of the first known conductive polymer is polyacetylene, and just due to this conjugation, which is the double bond, single bond, you can see the electron transfer to the electrode, and there is an electron movement on the chain, and there's a charge carrier to the reverse direction. So there is one necessity for the conductive polymers. You should have electronic conduction, but this is not enough for the conductivity. You need to dope with your counter ion your polymer. Of course, the other polymer, which is a polypyrrole, is very well known, very much used in this area, and besides its properties, there's a big disadvantage in this polymer, and we have been working in the conductive polymers area, and we have always seen that these are brittle and they have a hard processability. So this is the polypyrrole. You still have the conjugation, double bond, single bond, double bond is going to be the chain, and they have a high stability, as I said, and sometimes they claim that this is a biocompatible material for biosensing purposes. But the problem with these polymers are they are hard, brittle, and they have a very poor flexibility. So to solve this problem, you can prepare some nanocomposites. Of course, you will lose somehow their conductivity, and there will be some less brittleness in this case, and then you will be able to use for some certain applications, of course. As I said, you need some doping for these structures, and you can use some large doping agents, such as this one, which is also surface active reagent. You can use it in emulsion polymerization, and this has a long chain of alkyl chain, which reduces the interaction of polypyrrole chain between the groups of pyrrole units, and it somehow solvates the polypyrrole ring. So we use electrospinning. I just mentioned about this, was already mentioned by other speakers, and just briefly, you apply some high voltages between the two electrodes. One electrode is shrink of your material, which is dissolved in solvent, and you have the Taylor cone, and here you just come to the surface energy of your material, and then solvent dissolves, solvent evaporates, and you get the nanofibrous collections on the other electrode. So we use electrospinning technique. I will just mention about the acrylonitrile vinyl acetate copolymerization technique, which is a free radical copolymerization, very known technique, but we will use microemulsion or nanoemulsion, we call it. And then if you have tried some similar structure, metal acrylate, ordinary CO, the carbonyl group has a different position than vinyl acetate, so the comonomer is different. And then we just made the polypyrrole coating on these nanoparticles that we made by microemulsion. And then we separated these nanoparticles, used them for electrospinning purposes for the production of nanofibers. And then we have, of course, realized some characterizations, especially the reflectance FTIR, which you can just reflect the light and get some information of the absorptivity of some groups and particle size analysis, of course. So the emulsion polymerization is a well-known procedure, and we start with two monomers with some certain ratios, and then we use the surfactant, as I have shown you in the previous slide. In water phase, you form monomer droplets due to the surfactant, and then you add initiator. You have to increase the temperature to 70 degrees to form free radicals. So it's a free radical polymerization in emulsion media. And then after the particle growth, you get just latex formation, as you can see from the picture. In the beginning, you do not. There is no precipitation. You arrange the concentration of your materials that you will have a very stable emulsion system. Then we add pyrrole after lowering the temperature to the room temperature, and we can add different amount of pyrroles onto the system. As you might not see very well, but there's a color changes after 18 hours, so it's the end of reaction. Then we separate these particles by using ethanol and methanol, and then we take the SAM pictures. We see some differences. Of course, it's not very clear that we have very thin films, except the phase separation was happening in the two pictures. So the idea is to in situ polymerize pyrrole on the preformed latex, which is in the same medium without using any oxidant. So it's a coupling reaction actually. This one, the other one is free radical polymerization that I mentioned. What we propose, I will show you the details before. I will show you some mechanism that we think that this is the copolymerization takes into place in the presence of surfactant and in the hydrophobic part of the surfactant, of course, and we have the hydrophilic parts. When we add pyrrole at room temperature, when we lower the temperature, we get some absorption or some interaction between the sulfonyl groups of surfactant, and then we add some, we already have actually some APS, which is the oxidant in the system, and we get the polymerization around. It's a core shell structure actually. It forms core shells. So there is no precipitation during this process. I have shown you the picture of that solvent. We use FTIR reflectance spectroscopy for the characterization. These are the main bands. Of course, sometimes it's not, the changes in the absorbances are very low, so we prove that using the NMR, and these are the NMR results. The other one is determined by FTIR of forming these latex. And as I said, that the increase in some certain peaks related to pyrrole ring is around here, so there's not much changes. So the increased amount of pyrrole to detect very well. And this is the NMR spectrum of such core shell structure that we separated, and it's very obvious that we have the polypyrrole in the structure. And when we dissolve these nanoparticles in dimethylformamide, which is an organic solvent, we get, without any pyrrole, we get this type of transparent solvent. When we increase the pure content, you can see the color changes, and it's reflected to the UV visible spectroscopy. Around 430, we get peak absorbance due to the polypyrrole transitions from valence to polar states. So in the presence of that insulating polymer, of course. And when we prepare the electrospinning, I will show electrospinning conditions, nanofibers, which is corresponding to each solution, you can probably see the color changes. There is no color here. When we increase the pure content, you have the color of polypyrrole, which is a colored structure. And if you compare the absorbances, which is obtained from the solution directed by UV visible spectroscopy, and the absorbance which is obtained from the FTIR, ATR, which is the reflectance spectroscopy, there is a similar trend showing that the polypyrrole is in the structure of our system. And we look at their for the thermal properties. Of course, TG is showing their thermal behavior, and due to stain hindrance of polypyrrole, we depress the mobility of these chain segments, and this raises the TG value. There's an increase in the TG by increase of pyrrole content. And this is, again, dynamic mechanical analysis. We prepare some films rather than nanofibers. I will show you some DNA pictures of graphs of nanofibers as well, but sometimes it's difficult to get reliable results. And to show you the thin films of these materials, you can see the peak maximums are changing, but there are some, it's not the case that you get from other thermal measurements because you apply some forces during the heat application. We check the viscosities of these materials. The molecular weight is around 380 kilogram per mole, and without pyrrole we have such viscosity value, and if you increase the pyrrole content, you can see that there is a decrease in the viscosity of the system. And this was reflected to the fiber diameter as well, and these are the particle sizes without pyrrole and with pyrrole. There are some differences, and this can be expressed as phase segregation differences for the time being. And we did some particle size measurements. You see without pyrrole we get this size of nanoparticles, and it uses the same time for all cases. That's why we get higher sizes. And if you increase the pyrrole content, you increase the size of the particles, as you can follow from this. And this is the dynamic mechanical analysis of these composites, that you can see the toughness is increasing by the presence of fibers in the structure. And we have done some preliminary work on the impedance spectroscopy, which was mentioned today, and you can just get some specific capacitance value, which increases surely by inclusion of pyrrole, but it's not really probably sensitive to the from one concentration to other concentration. We need some further study in this direction. So this is the electrospinning of nanofibers. These are the conditions. 10% of solvent was used, applied voltages is like this, and this is the tip collector distances. So without pyrrole and with pyrrole, you can see the nanofiber formation. When we look at their SAM pictures, without pyrrole, you get these, and you can decrease the fiber diameter, as you can follow from here, by increase in the amount of fiber content in your system. And nanofiber diameter and pure heat mole fraction from the beginning is also related to specific viscosity of the solvent that you use for the electrospinning condition. So it's very reliable data, I think. And when we look at the film's conductivities, this is obtained from dielectric spectroscopy, so it's just conductivity on AC conditions. And you can see that at high frequencies, some conductivities in the range of 10 to minus 5. It's not too conductive, of course, for the time being, because we are using less amount of fiber, this very low amount of fiber content. Another copolymer that we use methyl acrylate. The only difference is the position of these two groups. The carbon should be here in the density. So we just wondered what type of effect we can obtain. We use a different combination, concentration of comonomer. You can follow from here. This is the potassium sulfate, and that's the surfactant that we use. And this is again the same conditions. Without pyrrole and with pyrrole, you can see the differences of the segregation problem. And we try to use some high concentration of pyrrole in this case, because in the previous case it was precipitating. In this case it didn't precipitate, and we just separated into two parts. I will show you why I just separated them. You can see suddenly increase of pyrrole when you go to the 30%, 30 microliter, not percentage, this is microliter of pyrrole. We suddenly got large sizes of particles. So it was interesting, and we conclude that this is due to aggregation at this point. So there's not a still precipitation, but there's an aggregation because it's not reasonable to get that size, which is micron rather than nanometer. And then we started to work in the first region, let's say. This is the same type of characterizations that we use by FTIR, reflectance spectroscopy. That's a very good technique and easy to get the characterization from solid surfaces with the little amount of material. And this was just the first copolymer was prepared, and to show us that there's a copolymerization. And when we include the pyrrole, we can follow the pyrrole changes by the absorbance ratio according to the versus the pure content, and that's the absolute value. To obtain the absolute value, we get some ratios of certain functional with absorbances. So it's a CC over CC plus CN. So CN is the acrylonitrile, the other one is. So we use this type of technique to get the quantitative, more quantitative data. And that's the increase of fiber. You can see some peaks coming out in that range. And that's also related to the pure amount. There's a linear relation, almost linear relationship. And you can also, particle size and absorption are also interrelated somehow. And these are the films that we obtain from different concentration of pyrroles, addition of pyrrole. And you can see some dynamic differential scanning calorimetry of that type of nanoparticles, and TG is increasing by the increase of pyrrole content. And this is dynamic analysis of mechanical analysis of films, and there is an increase in the Young modulus, certainly by the inclusion of pure. And when we did electrospinning under these conditions, which is similar to the previous one, actually, we get such fibers without pure, and if you have high amount of pure, we get a different morphology. If you have a high concentration of pure, some porosity is happening in the structure, and we are trying to understand that one. You can probably easily see that differences without pyro, and with pyro we have some porous structure obtained. This is the dynamic mechanical analysis of nanofibers. As I said, holding the fibers are a little bit difficult, so we use some banding of 4 times, and it's not stick with lighting again, just repeating these measurements, and we are trying to get some dynamic mechanical analysis results without and with pyro content. And that's, I think I already mentioned that these composites are core shell structures, and we can in situ polymerize the pure after the formation of these copolymers, and it's really directly reflected to the polypyrrole content when we get some properties and such as impedance properties and dynamic mechanical analysis. So you can see the only difference between the comonomer that we use, these omega acrylate is more better than I think of vinyl acetate, and the acrylonitrile vinyl acetate is used in the textile materials. So I like to thank my students, and this is Istanbul from the 16th century and today's Istanbul. Thank you very much.
Okay, any questions? There. Okay. Do you have an idea about the mechanism for the deposition of the pure on the fiber? This is precipitation?
No, this was in situ, actually. This was just
why
done.
do you get the pure on the fiber?
No, it was just done in the solution. We formed the particles in solution, latex formation, and we add pure into this medium.
Yeah, I understand.
And pure is absorbed on the surface.
So it's absorption.
It's first absorption of one, of course, and then due to the presence of oxidant in the medium, which is potassium persulfate, it starts to oxidize the carbon. I just showed you the mechanism at the beginning that we proposed for the time being, of course. Yeah, that's one. Pure is absorbed on the supernucleus, which is the hydrophilic part, and then polymerized on the. Of course, this is not in one direction, but it's two-dimensional growth of.
How does this compare with electropolymerization?
So we are doing electropolymerization very much.
So what is the advantage of this technique?
As I said, it's a brittle material. If you make a polypyrrole on the surface of your electrode, it gets soft. So it's very brittle. And in this case, we lose the conductivity, of course. As I have shown you, it's about 10 to minus 5. Even though
this is not brittle. This one is not brittle.
This is very just good, nice nanofiber mat that we obtain.
So do you understand the reason for that? Why is it so?
It's just
It's the same material.
It's just related to this structure. Probably
It's
related to the
related to
previous
structure.
talk today. There's somehow it's a nano-engineering actually. You form very controllable surfaces when we separate these particles. Each particle has the same content of polypyrrole.
Okay.
It's not a bulk polymerization. That's one advantage. In electrochemical polymerization, you get cross-linking at the same time. You do that.
Okay. Okay, cross-linking is okay. Good. Okay, good. Thank you. Thank you very much.